this screencast, we're going to take a look at oxidation reduction reactions, just a real brief overview of what they are, and some of the examples where we see them here in the beginning of the study for AP Chemistry. Oxidation reduction reactions, also called redox, are reactions that transfer electrons between the reactants. Just as an example, oxidation is the loss of electrons. So whatever substance is oxidized is going to lose electrons, its charge is going to become more positive, and the substance that's reduced, it's going to gain electrons, and its charge or oxidation number is going to become more negative. You'll hear the term oxidation state. It's also called an oxidation number. It's a positive or negative whole number assigned to an element in a chemical formula based on a set of rules. The rules are published in our book and can also be found in other spots, but the important ones, for example, are oxygen is always going to be a -2 oxidation number unless it's in a peroxide. O2 minus 2 is the formula for peroxide, and then it's going to have an oxidation number of -1. Hydrogen, on the other hand, is usually going to be a +1, except in the hydride ion, where it's going to be a -1. And then the oxidation number of chemicals or elements within formulas, they have to balance 0 if it's in a balanced chemical formula, but if it's in an ion, then it needs to add up to the ionic charge. And if you need help with this, let me know. More than happy to help you out figuring this out. Just ask, and we'll get you some help. Okay, so let's take a look at an example of this. One example is going to be a single displacement reaction. So in a single displacement reaction, we're going to have a more active metal displacing another element. So for example, if we were to take magnesium metal and place it into a solution of zinc nitrate, the magnesium metal is going to displace the zinc, so we're going to end up with zinc metal and then some magnesium nitrate in solution. And so the net ionic for this, since the nitrates are soluble in solution, we would have magnesium plus the zinc ion goes to zinc metal and the magnesium ion. Now in this case you can see that the magnesium is changing from a 0 oxidation number to a +2, so it's being oxidized, while the zinc is going from a +2 to a 0, so it's being reduced. So there's a redox reaction as it's taking place there as we see it. One of the more interesting types of single displacement reactions is with an active metal and an acid, and when you take a look at an active metal and an acid, you're going to get hydrogen gas being produced out of it. For example, if we were to take magnesium metal and add it to hydrochloric acid, you can see what's going to happen. The magnesium metal is going to displace the hydrogen, and we're going to get hydrogen gas as one of our products. I'm kind of out of space here, but our other product would be magnesium chloride, which would be a soluble salt. So we can get the production of a gas there too in that process. Our book has an activity series posted in it, so the ease of oxidation is at the top. So if the metal is higher on the list, it's going to be oxidized, and the stuff lower in the list is more likely to be reduced. So the ions at the bottom are more likely to be reduced. So if the metal is higher on this list than the metal ion, then the reaction, the way this looks, an activity series is a list of metals, and it's ranged in order of decreasing ease of oxidation. So any metal on the list can be oxidized by the ions that are below it. So magnesium metal here can be oxidized by any of these ions that are lower down the list. Right? So hopefully that's helpful, but it won't be oxidized by anything that's above it. Okay? so that's how we use an activity series. Combustion reactions also are a form of redox. In this case, the Bunsen burner flame uses the fuel methane, combines it with oxygen to make carbon dioxide and water. So combustion reactions of hydrocarbons under ideal situations will give carbon dioxide and water. If it's limited O2, then we won't get the carbon dioxide, but we will get carbon monoxide as a product, in this case, CO, not CO2. And that's pretty important to know. So if it's limited oxygen, we'll get carbon monoxide, and it's very limited oxygen, we'll just get carbon. We won't even get the oxide of the carbon, we'll just get elemental carbon or soot. Again, if you have questions on this, please let me know. I'm more than happy to help you out with trying to figure out redox and combustion reactions, and we'll take some time to work on these in class. This is just some of the background, and maybe it clears up a couple of the questions that you have. We'll talk to you again soon.